Now we'll look at the ideal gas laws. First of all, the work done to compress a gas. Here is an ideal gas in a sealed container. Now, look up what an ideal gas is if you don't know. There's the cross-sectional area of this container. And what I want to do is put a device, it's called a piston, on top so that I can compress that gas. So we will apply a force and compress the gas. Now when we do, the piston has moved through a height h, or a distance h. Now I want to find the work that is done. Very simple. Work is equal to force times distance, or in this case, the force times the h, the height that it moved through. Now recall that pressure is force over area, therefore force is pressure times area. Very important. And what we will do is take this pressure times area and put it in for the force. Something very easy to do. So now I have the work equals PA times H. But look at A times H. A times H, the area times that height, is the, can you finish the sentence? The area times that height is the volume. The work done is pressure times the volume. Now, it turns out that if the pressure is kept constant, that PV equals a constant. You can do experiments and you can confirm that. And you can do experiments to show that if the container has a constant volume, pressure over the temperature also equals a constant. And experiments can also show that the volume over the temperature is a constant. So we'll put these three results together into these ideal gas formulas. The first one, PV equals nRT. P is the pressure, V is the volume, and N, notice little n, is the number of moles of gas. And this is the most common formula I think that people use. They'll do it in terms of moles of gas. And R is a constant that would be given to you on a sheet. You'd never have to memorize it. And it's the one that goes with N. And then T, always, always, always in kelvins. The temperature in degrees Kelvin. PV equals nRT. The other formula is PV is capital N KB times T. Well, the only thing different here, N, is this time the number of molecules, not the number of moles, the number of molecules. And KB is called Boltzmann's constant. It also is given to you. The K in these formulas is the Boltzmann's constant. And of course, temperature is still in Kelvin. The other relationship is this here, and this helps you solve things by ratios. Try a few questions and see how you do. Now, the kinetic theory of gases. You don't have to memorize these assumptions. Just be aware of them. Molecules move in continuous random motion. Pretend I have them all contained in this container, and there's lots of molecules moving in every different direction. But the separation between them is very large compared to their size. And that means that because they're so small compared to their distance apart, they don't interact with each other with electrical or gravitational forces. These are all assumptions. And any collisions, whether it's molecule to molecule, molecule to container, are elastic, meaning kinetic energy is conserved. Now here's a formula that can be derived by Newton's laws and applying all the different laws to these assumptions. But what we will do is memorize it. This is the internal energy, U, the internal energy. And the internal energy in a gas is 3/2 N, we've seen this before, number of moles, R, that constant, and T in Kelvin. U, 3/2 nRT. To memorize this, here's an intern in a hospital. An intern, internal energy. And here's a tree. But there's a tree half. So there's a tree half, And this intern is trying to figure out what's wrong with this tree. Because what happened is a hen came in with a paintbrush and nailed an artwork and started drawing pictures. So you have this intern, the tree half, the hen, and the art. Notice it's spelled A, capital R, capital T. So you have the internal energy is tree half, hen is the N, and the artwork is RT. Now what you do is you talk through the picture a few times, look away, and cite it again, then write down the formula several times. Next, VRMS. RMS is root mean square. And this you think of as the average velocity of these molecules in a container that's moving around. And the average velocity is root 3kT over m. Let's go through this again. VRMS, root mean square. Again, m is the mass of a single molecule. K is that Boltzmann's constant. T is the temperature in, obviously, kelvins. Now let's memorize this. First of all, a car comes zipping in, and it goes vroom, vroom. Well, vroom, vroom, there's some vrooms there. That's VRMS. VRMS is vrooms. Now, the reason he stopped, and he saw this gigantic root beer can that was growing, and root beer is root, growing from a tree. Root tree. And he couldn't believe this root beer can growing from the tree, but even more amazing, underneath the tree, sitting there, is Kate Middleton. And Kate is spelled K-A-T-E, and that'll remind you of the K and the T, and she's from Britain, that'll remind you of the B. Kate Middleton, and she's standing over a whole bunch of M&M candies. She just eats them all the time. Over the M&M candies reminds you of over M. Now again, talk through this picture, mentally see each part of it, and then look away and reconstruct the picture, then write down the formula several times.